Yeah, we.
Okay, cool. All right, let's begin. Okay, so this workshop today is about a very, very broad topic in machine learning and especially deep learning that we call attention mechanisms. Attention mechanisms are kind of a tool you can use within a model architecture to boost performance, boost efficiency, and get a lot out of your model that you maybe couldn't otherwise. And kind of the interesting thing is attention mechanisms, sort of unlike any other architectural change you can make to a deep learning model, crosscuts almost all of deep learning. So you see attention in reinforcement learning, you see it in natural language, you see it in vision. And so I'll go through a few attention mechanisms today that I think represent a good survey of what attention has become in general. But really next week, I think Alexi's teaching a workshop on the transformer, and you'll really get to see the power of attention applied to sequence processing in specific. So with that, let's get started. So for our agenda, first thing I'm going to talk about is what is attention, and then I'm going to talk about the classification of attention mechanisms into what we call hard and soft attention. We're going to talk about attention for vision problems and some solutions that have been designed there. We're going to talk about a paper called Attention is All You Need. This introduces an architecture called the transformer, which pretty much underlies a lot of the state of the art for many problems, not just in natural language, but some other stuff too in time series processing. And then we'll talk about an improvement on the transformer quickly at the end called the performer. That is, I think, a month or two old, so it's very recent work in transformers. Okay, so first thing, what is attention? What is attention? Attention mechanisms are really built off this notion that some parts of the input are more important than the others. So for example, if we're trying to get at general scene understanding, the color of a wall behind a person is probably a lot less important than what the person's doing or other features about a video frame or an image of a person. So the idea is to, at a very high level, give little or none of the model's attention to the unimportant parts of an input. And a lot of what we're going to be talking about today is designing ways to do just that. So attention mechanisms are really about structuring and architecting computation within our machine learning models to adhere to this idea. And I have an image here of saliency, which is, I talked about this a bit in the fairness workshop if you guys attended that, but it's the idea that you can kind of look at where your model is looking to make a prediction, and attention mechanisms allow us to do this really well. So this is a visualization of where an attention model is looking when it's classifying an image of a boat and an image of a cat. And you can see very clearly what it considers to be relevant to the classification. And we'll kind of get in today as to how that works. Any questions about attention at a high level before I move on though? Okay, yeah, that's just the intro as expected. Okay, so really attention mechanisms can be thought of in two separate ways, and they generally fall into these two categories. And we call those categories first hard attention and second soft attention. So hard attention is probably a little bit more intuitive. It's kind of, we decide an input location to attend to. So if we're working on images, if we're working with an attention mechanism in the visual domain, we may decide a 3x3 pixel grid to attend to. And we just feed that 3x3 pixel grid into our model, and it does something with it and whatnot. And we then repeatedly update the attention location to gain information. So maybe the attention model will start off scanning the middle of the image, realize it's looking at a face, and kind of track through the face, telling the input to give it, the next 3x3 grid and the next and the next and the next. And it kind of goes this way, a lot like how human eyes would, right? Like if you actually track someone's attention and where their eyes are looking when they're looking at a natural image, it tends to track the subject very well, much like attention models learn to do. But we have a problem. I said that hard attention has this thing where we decide an input location, but how can we differentiate a decision? Does anyone have any ideas? This is kind of a very fundamental problem with hard attention that is worth bringing up right away. How can we differentiate a decision? It's fine if no one has any ideas. This hasn't come up in any workshops yet. Okay, so the thing is we can't really. The problem with hard attention is that it gives us something that is non-differentiable. You guys have probably been learning this whole semester in your workshops about how, you know, you take some prediction, you apply a loss to it, and then you differentiate this loss. But how can you differentiate whether or not where you're looking is the correct place to look? And the answer is you can't in general. So we rely on reinforcement learning. If you've heard of reinforcement learning, great. If not, I think Joey Hain is going to teach a few workshops at the end of the semester about it. So yeah, I'll get to more of how that looks in a second. But on the other hand of hard attention is soft attention. So soft attention says we compute a weighted combination of input locations with coefficients predicted by an attention mechanism. So instead of just picking one 3x3 grid, maybe we weight all the 3x3 grids that we could take, combine them together with a sum, and that's the input to our model. And in this way, we can backpropagate directly into the coefficients, and we don't have this non-differentiability problem. And then some benefits of attention in general are one that they encode the idea that some input locations are more predictive than others. In this way, they can be robust to changes in irrelevant regions. So you saw the picture of the ship being attended to in an earlier slide. Let's say the ocean was like, I don't know, 10 points higher in RGB, like it was just brightened a lot. That could throw a lot of models off, but attention models that actually don't even take that into account will be robust to changes like that. Efficiency, so attention models don't need to look at the entire input. And especially for really, really large inputs, the forward pass latency can be a lot lower. And saliency, right, I talked about this briefly. Attention models tell you exactly what they looked at. One of the papers we're going to look at in a bit shows us how they interpreted their mistakes very easy. You can see exactly what went wrong at what point just by looking at what was attended to. So before we move into like the actual specifics of certain attention mechanisms in deep learning, does anyone have any questions about hard or soft attention, attention in general?
Yeah, what does it mean for forward pass latency to be low?
Yeah, so when I say that, I just mean like actually getting a prediction out of your model doesn't take that long. So it can be like 2 to 10x faster, which is, you know, a big speed up if you're trying to like deploy on an iPhone, for example, and you want like real-time answers.
Okay,
Does that make sense?
yeah.
Any other questions?
This was kind of from the previous part. Wait, I didn't understand how soft tension became differentiable.
Yeah, it's essentially like, let's see, it's essentially, and I'll show more of the math of what this looks like later, but let's say you had something predicting coefficients for this sum. So maybe you have two patches of the images, two patches of an image. In hard attention, you would have to decide which of those patches to look at. In soft attention, you weight those patches and add them up being multiplied by their weights. So maybe you do 0.5 and 0.5 and you're just averaging them. Maybe you do 1 and 0 and you're just choosing one essentially. But regardless, if you pick those weights for the combination with, for example, a neural network, then you can differentiate with respect to those weights and then differentiate with respect to the weights in the neural network that chose your combination weights.
Wait, so are these weights assigned to the regions of an image, for example?
That would be, yeah, that would be a good example. So to be clear, these weights that perhaps weights isn't a good word because that gets kind of overloaded between the model and what I'm talking about. I'm talking about the coefficients of the combination. those will get assigned to a specific region. Yeah. So like maybe we have 100 patches of an image. We assign them all coefficients, multiply them by their coefficients, and add those all together. And it becomes sort of like a weighted average
And so
of patches.
we learn the coefficients then.
You do not learn the coefficients directly usually. You instead will, and I'll show this, you will learn the mechanism that predicts the coefficients.
Interesting. Oh, right, that makes sense. Okay, cool.
Yeah. Any other questions? Awesome. Okay, so we'll get into some actual like models that are built on these ideas of attending to a specific part of the input. So the first two models that we're going to talk about were by the same group, I think at Google. And they're trying to solve the problem of image recognition generally. So that can be classification, that can be object detection. In this paper, they're mostly focused on classification. So they're trying to classify the object in an image. And so their formulation of this problem is we can treat the recognition problem as a sequential decision problem. And I have in parentheses RL. If you haven't seen reinforcement learning or RL before, don't worry about it. But if you have seen RL before, that's what you should immediately be thinking when you see sequential decision problem. Essentially, we train a model to make a series of decisions about where in the input image to look, so that it gains more information about what the true class of the object might be over those glimpses at the image. So kind of more formally, we set up the problem by saying an agent, meaning our neural network, observes n glimpses of an image by deciding where to attend. The glimpses are encoded by 2 linear layers and then fed into a recurrent neural network for processing. Just because I can't remember, did you guys learn about recurrent neural networks in a previous workshop?
Yeah.
I've seen, okay, cool, awesome. So maybe this is fresh, but yeah, so we encode glimpses of the image, which are essentially a patch of the image that the model has decided it wants to sample. We feed those into a recurrent neural network. At every time step, the recurrent neural network outputs 2 things. It outputs a classification of the image given what it's seen so far, and it outputs where in the image it wants to look next. So maybe it starts out looking in the middle of the image and it sees something that like doesn't look all that interesting. So it decides, okay, I want to look somewhere, on the side of the image. Maybe the subject is on the side of the image. And so it defines the next attention location based on where it thinks it can get the most information out of. And then this is all trained via something called policy gradient methods to address the non-differentiability. What I mean by that is it's making a decision as to where to attend next, which patch of the image to look at next, but we can't really say, like, us as humans, we don't really know where the correct patch to look at is. So we can't give it much feedback there. We can't say, oh, well, you probably should have looked here in your 3rd iteration, because that's not really helpful to the model and it would probably constrain the model to think exactly like how we do. So since we can't give it any signal directly, what we do is we say, at the end of it all, once it's looked at n patches and made those n decisions as to where to look, and then it outputs its final prediction, we give it a reward of 1 if it got it correct and a reward of 0 if it didn't. And how do you actually like back propagate this and train your model with this? I'll leave that for Joey Hayna to explain in the reinforcement learning workshops, but if you've heard of reinforcement learning before, we just apply a policy gradient to this and train it that way. But what you should really get out of this isn't necessarily like that we train it with RL or anything like that. It's more that our model is choosing where to look in the image in these very small patches, and then updating its choices as it sees more and more information about the image. Yeah, and I have the reward here. So what does that actually look like? And I'll take questions after this slide if you're holding on to anything. So we have essentially 3 building blocks of a model like this. The first is what we call a glimpse sensor. So this receives a location. Remember, the model predicts, or it tells the next time step that it wants to look at some location that it thinks might have relevant information. So we have a glimpse sensor, and this glimpse sensor, all it really does is it samples the image around this location at 3 different sizes and then resizes them. I don't know how well you can see it here, but it samples really small on the tail of this 5, kind of medium, so that it gets about half of the body of the handwritten 5, and then it does a really big sample so that it gets the whole 5. So it sees this image patch at different resolutions and kind of tries to get more global information combined with local information in a glimpse. So all the glimpse sensor does is it takes a location, makes these 3 samples, and then puts them into a vector. The second part of this kind of goes along with the glimpse sensor. So we have the glimpse sensor that gives us our patch that we want to attend to. We have our location that we gave to the glimpse sensor as to where to attend. And then these get multiplied by some vector. So what this is showing is just your average feed-forward neural network layer, just a linear layer attached to both the output of the glimpse sensor and the output of, attached to both the output of the glimpse sensor and the location. And these encode this intermediate vector that kind of gives us an idea of both what the glimpse looks like and where it was. So this is useful for the model to use. And then this is the complete model. So we have our glimpse sensor right here. I hope you can see my cursor, but everything I just talked about in these 2 images before is right here. G of t is essentially the representation of our glimpse of the image, where we're attending to, and what it looks like. And then we feed that into our recurrent neural network. And out here, you can see it outputting both a prediction at that time step, given all the information it's seen so far, and the next location it wants to attend to. And we just come back here and do the same thing over and over until we've gone through our max steps, and then the final prediction we have is the best we can do. And that's what we say is in the image. Does anyone have any questions about this model? It may be a little unlike something you've seen before.
Those 3 boxes that you said, those where it took those little like small kind of sections of the image, where did those boxes come from? Did it learn those boxes, or was that just like a random location to start paying attention to for it?
Are you asking? Okay, so
in the
are you asking the first place we attend to, or are you asking how on each iteration we choose where to attend?
No, the first place to be attend to.
Yeah, I actually don't remember. It's been a while since I read this paper, but I believe you can either, and actually the next slide discusses this a little bit, but you can either just always start off in the middle, with the intuition being like most interesting things are in the middle of the image, and then have future glimpses move around from the middle, or you can do it random, or you can have some sort of network predict the initial place to start, which is what the model in the next slide does. Regardless, you're going to start somewhere, and after the first step, the model will be in complete control of where it looks next. Does that answer your question?
Yeah, it does. Thank you.
Cool. Any other questions?
Wait, Joy, can you explain like the location going into the glimpse sensor again? I'm just not sure, because I thought the glimpse sensor will like find where the location is.
Yeah, so the glimpse sensor, the location is really just an XY in pixel coordinates. Glimpse sensor is kind of like a fancy word that they used for, all it really does is it crops the image around the XY you give it. And it crops it at different sizes to give us like both local and global information. But the glimpse sensor isn't learning anything, to be clear. They call it a glimpse sensor, I guess, to be formal about it, but all it really is it's just kind of like cropping at 3 different sizes around the location you gave it. Does that answer your question?
Okay, yeah, thank you.
Yeah, so nothing's learned in the glimpse sensor. Any other questions about this model in particular?
Wait, I guess one question is like you mentioned that attention is normally more efficient, but then if you look at this, like, isn't each sort of cell basically outputting 3 images that then need to be classified? Wouldn't that make more computation instead of like sort of like one-shotting it with a CNN?
Yeah, good question. So 2 things there. One, attention, maybe I said is usually more efficient, but I think a better way is can be more efficient. So not necessarily is it always more efficient. Sorry if I was confusing about that. In this case, I think this one can be more efficient than a normal CNN because the actual inputs are very small. So when I say glimpse, this ends up being like a 5x5 or 9x9 region of a much larger image. So it's taking in a much smaller input, which means it has many fewer parameters, meaning it has to do a lot less computation. So while it does have to go around multiple times and do these forward passes and then predict the next place to attend and then forward pass again, it's operating on much smaller images and like glimpses of the image. So it ends up looking at only a fraction of the actual image. And I think in this paper, they did like, I think they let the model have like 3 or 4 glimpses. So it's not doing this that many times. And in each time it's looking at a very small piece of the image. So I would say this can be more efficient because it's doing more forward passes, but each forward pass is so much faster that you kind of have competing objectives here, but the fact that the forward pass is faster ends up winning. Does that make sense?
Yeah, cool. That makes sense. Thanks.
Yeah. Other questions? Awesome. And then here's a follow-up paper, or this is an image of a model in a follow-up paper by the same group, kind of building off of that last model that we showed you. And here this addresses Devang's point exactly. Where do you start? There's actually a few layers here that encode a kind of what they call like a coarse grained context of the image, and it tells the model where to start. So you can see here, it doesn't get any glimpses on the first one. It just predicts a location. And then that location is where you start attending to. So that's one optimization they made. They also have what they call an emission head and a classification head. The emission head tells you where to attend next. So it's exactly like before, it's telling you where to look next. But the classification head happens earlier on in the model. And that predicts just like the object class, like I said before. The reason for doing this is they found better results because they're feeding this context, like I mentioned, to initialize the attention into the emission head, because they want it to emit a reasonable first location without needing any glimpses first. That being said, if they had just stacked this all together and put the classification head somewhere out here, the classification could be really highly context dependent, which is something they found weakened the model's ability to generalize across scenes. So classification would learn like not necessarily to look at just certain parts of the image, but it would look at the encoded context of the image, which is global. And that's kind of cheating your way around the attention mechanism. So they found a lot better performance when they made this optimization of removing the stream of information from the encoded context from the stream of information embedding the classification. So these are just kind of like 2 small optimizations to the model we saw last slide that increased performance a decent amount. Any questions here? I know that was kind of a hand wavy explanation.
So if we didn't have this thing that we just added in the beginning, I guess, would it be correct to say that one disadvantage of the previous model was that it never took into account context that much?
It takes into account context. It's just that the thing is that this context is global. It's a context of the whole image. So it has that advantage.
Right.
So I would say yes, sort of. Like that's probably a good way to think about it. It's just that like that context shouldn't be thought of as informing the classification down the line. It should only be thought of as informing where to look, if that makes sense.
Yeah.
Cool.
Wait, but why can't it inform the classification?
Well, then you're kind of cheating the attention mechanism, right? Then you're just using like essentially a normal CNN for classification.
Alright.
And then it's, you lose some of the benefits of like saliency, for example. You can't see exactly where the model looked to make its decisions.
Right. Okay, cool. That makes sense.
Yeah. Other questions? Cool. And here are some of the results. Like I said, so I think in this one, they are giving it, let's see, 1, 2, 3, 4, 5, like 5 or 6 glimpses. And in this one, they're giving it 3 or 4 glimpses at the image. And you can kind of see where it tracks around the image, where it decides to look. So on the 8, its initial glimpse sees that there's kind of an 8 in the bottom corner of its of where it's looking. So, or not an 8 necessarily, but it's something. So it decides to move down and kind of go around this 8 and attend to the areas around the 8 to classify it as an 8. The 2, kind of a similar thing. It kind of starts out here in the middle of nowhere. And then it kind of goes around the 2 and absorbs the structure of the 2. And you can see in these in the rows of this picture, kind of what it's seeing as it attends to new locations. Any questions here? Cool. And this is kind of addressing the point of saliency that I made before. It's very easy to tell what the network was looking at when it made its decision. Okay, so moving on to another model for visual attention. We're going to talk about captioning now. So the authors of this paper are trying to solve the problem of, given an image, write the text that you might caption it with. So if I have an image of like, I think there's an example on the sides of a woman throwing a Frisbee, the ideal caption would be something like a woman throwing a Frisbee in a park with her dog or something like that. So that's the problem they're trying to solve. And kind of back to soft versus hard attention, one problem with hard attention is, like I mentioned, we need RL to train it. And it can be really difficult to train in an RL framework. Yi and I were joking about this workshop about making you guys train something with hard attention, but we felt like that would be cruel because RL can be just that finicky. So kind of like trying to find a way around RL, you might turn to soft attention. And that's exactly what this paper does. So the idea is to use the output grid. Like if you're trying to caption an image, use the output grid of a few convolutional layers as image features. If you guys remember from your workshop on CNNs, if we pass an image through a few convolutional layers, you'll get a much smaller grid of pixels, but each pixel is kind of the result of processing a bunch of pixels in the image. We call that the receptive field, if you guys have heard of that. And each location in the grid may have a receptive field that is the size of a small to medium patch in the image. For an example, if you look at this image, we see the receptive field after the first layer of the ConvNet is really looking at like this whole area over here. And then maybe we downsample with like max pooling or something like that. And you can see like what you get is a kind of small region in the features can correspond to a much larger region in the image. So you can have this grid that is actually quite small, but each member of the grid has a receptive field that is maybe a bigger patch in the image. Does that make sense to everyone? Any questions there? Okay, and then now that we have this representation, now that we have this grid of features that can kind of be thought of as patches, we do a very similar setup as before. We take n evaluation steps and have an LSTM predict the next word in the image caption at each step. And not only that, we have a separate prediction head or attention head that predicts the new attention weights or coefficients for the patches given the LSTM hidden state. To be clear, did you guys talk about LSTMs yet in the workshops?
Yeah.
Cool. So you guys understand like the hidden state and the continue state and whatnot?
I think so, yeah.
Okay, cool. Yeah, so given the hidden state, we want to predict attention weights for the next state. To put this mathematically, because that sentence is kind of a mouthful and I think it's a little bit easier to understand, the input to the LSTM is a combination of the patches in our feature grid. And I'll have a diagram in a second of what this looks like that might be a bit more clear. But our input xt is just the summed combination of all the patches. And at each time step, the LSTM predicts AI t for each I. The attention weights are computed via some function f that computes attention weights. In practice, this is like a 2 or 3 layer neural network that's just attached to the LSTM. It predicts the weights for each patch given the hidden state of the LSTM. And then, have you guys seen softmax in the workshops yet?
Yeah.
Sorry?
I think we
Yeah.
can over it, yeah.
Okay, so softmax, what we're doing here is we take all our attention predictions and then we normalize them so that they are all positive and add up to 1, making this kind of a probability distribution. So that's all we're doing is we have a branch to predict the next word in the image caption and a branch to predict our attention weights that we actually use on the feature grid for the next iteration, which predicts the next word. And here's kind of, the paper is pretty bad as far as detailing their model in pictures goes, but here's the best picture I could find in the paper. By the way, all the papers I'm referencing are linked at the bottom of the slides, and I'll send the slides out later. So we get an input image of a bird. We get a 14 by 14 feature map, each of which kind of corresponds to a patch of the image. And then our RNN, kind of sequentially processes an attention or a soft attention over these features, and then predicts the next word. So a, bird, flying, etc., and where to attend to next. And you can kind of see in these 3 pictures, the first thing it attends to is kind of the wings of the bird, then it attends to the body of the bird, and then it attends to the background. The attention, by the way, is the parts highlighted in kind of the white. So it kind of attends to the background once it starts getting towards like water, for example. And yeah, go ahead.
So you know how we have like n steps, right? It goes around n times, right? So
Yeah.
if we increase this n, can we get more elaborate with our description of the image?
Sure, to a point. Yeah, so n is a limit on your description length.
Right.
You could certainly hope that increasing like n to infinity might give you like a whole background on the story too, and like maybe it gives you like a paragraph or a whole story within it. But in practice, that probably wouldn't happen. It would probably end up spitting out gibberish. LSTMs have an issue, I think maybe they covered this, but they have an issue with long-term dependencies. So the hidden state gets kind of like diluted and convoluted over time. So it's hard to process long-term sequences. One of the models we're going to talk about in a second, the transformer, was actually built in part to solve that. And it uses attention. So typically you keep n reasonably small, 1, because you don't want to spend a ton of time computing the caption, and 2, because you probably wouldn't get that much of better results from it. Yeah, does that answer your question?
Yeah, definitely. Thank you.
Cool. Other questions? Deevy's raising her hand.
Hi, yes, Stevie here. I was wondering what like the intuition is behind using the hidden state to predict the next like location.
Yeah. I mean, the hidden state is kind of like all you can really get out of an LSTM. There's the continue state as well, or the cell state, some people call it, but that has less processing done to it. I think in general, the hidden state of an LSTM is meant to encode like the history of processing of the sequence. So it should kind of intuitively encode where you've looked in the past and what information that got you, you being the model. And so the model should be able to, from the hidden state, know where it's looked, know the information it's gained, and therefore know what information it still needs about completing the sentence that is the caption, and where it should be looking to find that information. Does that answer your question?
Yeah.
Cool. Other questions? Okay, and this is kind of some of the results, and highlights a very important part of attention models, once again, is saliency. Here we can see exactly what was attended to for the underlined word. So when the model predicted Frisbee in the caption, this is where it was looking. It was looking at the Frisbee. So you can see it's learning something good. Same thing with the teddy bear. When it predicted girl, it was looking at the forehead or the hair of the girl. Yeah, and then on the right are two counterexamples. There are two examples that went poorly. So it predicted a large white bird standing in the forest when that is a giraffe, actually. But if you look at what was being attended to when it said bird, it's actually looking at the giraffe. So you as a model designer may want to use attention mechanisms to help with this sort of saliency. Maybe you look at this adversarial example and you think to yourself, okay, maybe I should have more giraffes in my data set. And maybe you go mine more data of giraffes or something like that. Same thing with this last example. It predicts that the object in the image is a surfboard, when in reality, I think it's like a kiteboard. Yeah, you could look at this and say like, okay, maybe the model hasn't seen a lot of kiteboards. So the whole saliency aspect of this makes models much more interpretable. And that's a big takeaway of attention in general. Any other questions?
Wait, I have a quick question about like the output of the LSTM, because you said like it would output like a sequence of words, but is that this sentence, or is it like the keywords, like the objects in the image?
Sorry, what do you mean by, is that the sentence versus the keywords?
Like, I don't know, because from what I know, like LSTMs, like you use like many to many. So like you pass in all of them and then you would get some output that's a sequence. But like, is that sequence like the sentence that's shown in the images here, or is it like a sequence of the keywords within the image? So like a noun, verb, and then something else.
Yeah, so it's the actual sentence you see here. I think what they probably do is classify over vocabulary or something like that as to what the next word should be. Yeah, is that answering your question?
Yeah, because that makes sense. Because I don't know, I was like wondering how you calculate a loss for a sentence. So yeah, that makes sense.
Yeah, I think there might be another workshop that touches on that a bit more in the applications workshop, but there are kind of some good ways to do it and some bad ways to do it. I don't really want to get into that now, but you could imagine just classifying it and using like a standard cross entropy classification loss to do it. But there are other good ways as well. Okay, cool. So other questions? We're going to be moving out of visual attention into two kind of quicker last topics. Okay, well, you can always ask questions later that refer back to other slides. So what we're kind of going to be moving into now is a preview of Alexi's workshop. I'm kind of hoping to get you some like early looks at what he'll be teaching you next week in transformers, because transformers, I've learned the hard way, are pretty hard to teach, and people need a lot of time to digest them. So don't expect that you will necessarily get this all now, but it's good that you see it now, because next week you may have a better chance of understanding it. In specific, we're going to be talking about a paper called Attention is All You Need. I've linked the paper. It introduced an architecture called the transformer. And the transformer is probably one of the most revolutionary architectures ever. If you've heard of it, you probably know how great it is. If you haven't, here's your chance. It's great. It's widely used in industry as well as academia, and it is the basis of the state of the art for many, many tasks. And most of the transformer is what we've been talking about today. It's an attention mechanism with a little bit of structure built around it. If you've heard of GPT-2 or 3, it's made the news quite a bit in the past 2 years. Yeah, 2 years from OpenAI, because they're able to generate very realistic sounding sentences and stories with a lot of like deep plot and background. And people are touting it as like the closest thing to fake news being generated that we've gotten to yet. I have an example in this image below, and I've linked this website in the slides. I went to someone's website who had taken a transformer called GPT-2, and they essentially have like made it available for sentence completion. So you can write a little bit of a story and it will complete the story for you. I wrote the opener to a Java program, and it wrote the hello world and instructions. You can see below the completed text. So in the text box here, I wrote public static void main, I know a lot of you are like freshmen, so you're probably in 621B and this gives you nightmares or whatnot, but what it did is it completed it. So all the text not in bold here is stuff it generated. So it gave me directions on how to compile and link my code. It wrote in some code for me, all that sort of stuff. And all that it has done is it's seen a lot of code before and been trained on a corpus of some code. And now it's learning to predict via these attention mechanisms in the transformer what it should be completing sentences with. So I think this is really cool. And in the next few slides, you'll get a sneak peek of like how that works, and more in the next workshop, you'll get to know exactly what's happening. So attention is all you need. The attention mechanism in the transformer is based on something that the authors call scaled dot product attention. And actually just a quick, I think we can do this in Zoom. Will you raise your hand if you've seen dot products before, like in a math class? I don't know what everyone's linear algebra background is. Okay. Looks like a lot of you. Cool. So one thing to recall, and if you haven't seen this, just take me at my word for it, is that a dot product, which is essentially a function that takes in two vectors and returns a number, can be a measure of similarity. So I have written out the dot product of two vectors here. This is one definition for it. So the dot product of x and y is equal to the magnitude of x and the magnitude of y multiplied by the cosine of the angle between them. Let's just assume for now that x and y are unit length, so their magnitudes are 1. Then really the dot product is just the cosine of the angle between them. So let's see, the higher the dot product, I'm forgetting how trig works, unfortunately, but the higher the dot product, the more similar they are. And we're kind of going to use that intuition to build up what attention might look like if we write it out in terms of dot products. But are there any questions here about dot products and how they represent similarity? Okay, so the idea here between behind scaled dot product attention is to treat attention as a key value store. If you haven't seen a key value store before, think of it as a hash map. I think everyone's probably seen hash maps maybe, or I hope so. If not, they essentially take a key and map it to a value, like a dictionary in Python. And what we really care about is we want to be able to query this key value store and get back values from the key value store, even if the key doesn't exist. So we want to query with a query queue and get back values for which the keys representing those values are similar to our query. And how we do that is we can think about it as like, let's encode these keys and these values and these queries as matrices. And then we can compute similarity between the keys and the queries as a row-wise dot product. So if a key is similar to your query under dot product, then we should probably take into account that key's value. Does that make sense at a high level to everyone? I know it's kind of like laying a lot of structure on it. So if you have any questions, now would be a good time. Okay, and feel free to interrupt me at any point now that we're kind of in this more, complicated realm. So yeah, all you really do is you measure the similarity between keys and your query. And if they're similar enough, maybe you take into account its value. And that's kind of like, this should be maybe the gears in your head are turning. This sounds like soft attention, right? We have attention scores for each part of the input, and we take into account that input proportional to its attention score. So for example, the keys and the values could be embedded parts of a sentence, and queries are embedded representations of verbs or nouns. So your query is like, I'm querying for a verb, and I've represented the notion of a verb as a vector. And then all the keys are parts of your sentence. So the keys are nouns and verbs and all other parts of a sentence. And under similarity, under dot product similarity, your query for a noun will match the keys for the nouns of the sentence. So maybe you look at the values of those keys and they're all the nouns of the sentence. This is used a lot in, transformers used a lot in natural language processing. That's why I'm using the example of sentence representations here. So now let's get more into the math. So for a given query matrix Q, key matrix K, and value matrix V, scaled dot product attention is defined as follows. So, and this is kind of where the transformer starts to get a little complicated. What we're looking at here is, let's break down what we're looking at here into pieces. So let's look at the Q multiplied by the K transpose first. In case you don't know, like I don't know what the linear algebra background of everyone here is, but K transpose will just make all the rows of K columns and all the columns rows. That's all it'll do. And hopefully you remember matrix multiplication. But essentially what we're doing here is matrix multiplying Q with K transposed. Since K transpose makes all the rows of K columns, and since matrix multiplication will multiply the rows of Q with the columns of K, we're essentially taking dot products between every row of Q and every row of K. And I'm just gonna think about that for a second, and maybe you start to realize, okay, that could be a measure of similarity. So we are essentially, in this first step of QK transposed, measuring similarity between every row of Q and every row of K. So we're measuring the similarity between all of our queries and all of our keys. Ignore this, divided by for a second. And then the next step is to take the softmax of that. Like I mentioned before, the softmax makes everything add up to 1 and be positive. So it's a probability distribution essentially. That makes it so we have like nice properties where when we take a weighted sum of things, we end up with a value that is what you may call like convex in its inputs. Don't worry about that if it doesn't make too much sense here, but just know the softmax will make all the values between 0 and 1, and all the rows add up to 1. The final step is then to multiply by the values. So we've encoded in our QK transpose softmax similarity scores between queries and keys. The keys are aligned with their values in terms of like which row goes where. So now we have similarity scores which represent attention weights. And we apply those attention weights to our values via matrix multiplication again. So what this step will do is it will take a weighted combination of all the values we have, weighted by how similar their corresponding keys were to the query we asked for. Okay. Any questions right off the bat?
Yeah, can you repeat what you just said? I'm so lost after that last sentence.
Okay. Yeah. So do we get how after the softmax what we have is a matrix of similarities between queries and keys?
Yeah.
Okay. Then let's see. So
Oh, wait. So 1 second. If I'm understanding this right, when we have the similarity score, the regions that have a higher similarity score, when they multiply with the value matrix, that value gets a higher value as well, right? Because it gets multiplied by the similarity score, and so that becomes the answer.
exactly. That's spot on. Yeah.
Okay. Thank
Yeah.
you.
So the first 2/3 of this is computing similarity scores. The multiplication by V is applying those similarity scores to the values such that values with keys similar to our query are weighted really high in the output, and values with keys dissimilar to our queries are weighted really low in our output. Does that, any other questions? Does that make sense? And once again, this is something that like I certainly needed to look at for a while. So this may take some time, and Alexi will go a lot more in depth with this next week. Any other questions though?
So how does this relate with like the attention we were doing before? I guess just what does like attention mean here?
Yeah, great question. And I probably should have stepped back earlier to explain this, so thank you for calling that out. This is essentially just attention applied in a different way, right? Before we were just, we were kind of using attention at a high level to say these values all get, predicted somewhere, and they get applied somewhere else. And then once they're applied, they're inputted to the model. What you'll see when you actually learn about the transformer architecture is that these Q, K, and V matrices are outputted by earlier layers in the model. So it learns what to query for, it learns the keys to query into, and it learns the values to return from these queries. So this is a little bit out of scope for this workshop in specific, but what you can think about is like if the input regions are the values and the keys are some notion about what that value might hold, and we learn what to query, we can query our key value store and just get input regions from our input that match what we've learned to query for in the input. So you can query for things like sentiment. People have analyzed these models applied to natural language, and some of the queries are like sentiment based. Some are queries about like what is happening in the sentence, for example, or what is happening in the image. But these are attention in really the same way. You're just restructuring the computation into matrix multiplication to kind of make things, I guess, both easier to read, and matrix multiplication is very fast to do on a computer. So does that kind of answer your question? It's essentially that we learn Q, K, and V, and then as a result, we're kind of learning attention in that way.
Okay, yeah. Wait, so for something like a query on sentiment, would each row of the matrix be a different sentiment, or would it just be like one row which means sentiment?
Yeah, the example I'm taking is that one row of K would be sentiment, and that the corresponding row or column of V would be the actual encoding of the sentiment. So when we query for sentiment, it's going to match up most with like the key that says, okay, this value represents some sort of sentiment about the sentence. And then once we go to multiply, the value that actually represents that sentiment will be really upweighted. So yeah, to answer your question directly, it could be, in the example I'm using, yes, it could be like one row. More generally, these are something that'll be learned by the model, and it's kind of hard to tell.
Okay, cool. Thank you.
Yeah, other questions? Okay, I'll keep moving, and this is something that you guys will get more practice with next week in specific. And lastly, to kind of touch on what I said to not worry about before, the term DK in the bottom ensures that values aren't too big in the softmax. I don't know if you guys were shown a plot of softmax ever or explained about the vanishing gradient problem, but if you've heard about vanishing gradients, this DK will just ensure we're essentially dividing by the dimension of the matrices, or one of the dimensions of the matrices, such that values to the softmax aren't too big and the gradients don't vanish. If you haven't heard of vanishing gradient, don't worry about it. But if you have, maybe this gives you a little kind of tidbit. Yeah, and I already touched on that. So kind of the last key part of the transformer is that we then take these attention layers, these scaled dot product attentions, and stack them in what we call multi-head attention. It's defined as this. Each head is just one of the attention layers we talked about before, and we just concatenate them and multiply their output by some matrix. And this is the fundamental building block for the transformer. So you just, much like, let's see. Oh, I guess I lost my bullet point on it, but maybe this reminds you of like in convolutional networks, how in each layer we stack a bunch of convolutional filters and their outputs. This is much the same idea here, is that we're just stacking outputs of a basic building block that we already know how to do, so that we can maybe have more diverse building blocks in aggregate. And then the next slide kind of addresses what we've just been talking about. So graphically, these look like as follows. The scaled dot product attention, which computes similarities and then gets relevant values, is right here. Multi-headed attention is really just stacking these and concatenating them. We have linear layers here to allow the model to kind of like learn more powerful representations, but the crux of it is that we stack a bunch of these in the first image. The last image here is part of the transformer. Don't worry about it for now. It's quite complicated. And it's actually much bigger than this. Over here you see nx, that means n times. Maybe you do like, I think BERT or GPT, if you've heard of those models, do like 12 times of this. So it's 12 of these whole pictures here stacked together, and these are all built up of you know, the multi-headed attention and the scaled dot product attention. So I hope what you've gotten out of like the transformers section here is that like what we can do is represent attention as matrix multiplication under the assumption that dot products tell us how similar two things can be. If we can encode things that we want to compare similarity of as vectors, we can use dot products to compute similarity and attend to regions that are similar to what we want to know about. Any questions about the transformer at a very high level?
Wait, so just to like clarify, like what we're training is how we convert like our input into those vectors, or is there something we have to train about the intention as well?
Actually, yeah, great question. Both. Alexi will touch on this more, but you end up learning both the QKV. Well, okay, so technically it's just the vectors, but how you actually apply the attention is reliant on these QKV, and you're learning these. You're learning to predict QK and V matrices such that attention works in a way that is beneficial for the model. So I would say you are kind of learning to encode what you want as vectors, but it's kind of more general than that. And I think that your question will probably be better answered next week. You'll probably get a much more satisfying answer. I don't want to dive too much into it if that's all right.
Yeah, cool. Sounds good. Thanks.
Yeah. Any other questions? All right, so we're just going to finish up with like one quick topic. I don't expect anyone to understand this super well right now. It's kind of just like, here's something that people are working on. The paper is pretty complicated. If you want to understand it, I'm sure you all could, but you'd probably have to read the paper because I've left a lot of detail out. So the idea here briefly is it's called performers. I'm going to put the attention we just talked about before up here for reference. But the problem is that this scaled dot product attention turns out to be kind of slow, especially when we have really, really long sequences. So if we're looking at like maybe an entire Wikipedia article, that's a pretty long sequence, right? That could be a really, really long Wikipedia article. And what happens is like these Q and K matrices turn out to have like kind of bad dimensions once the input size grows. I've listed their dimensions here. So if L is the length of the sequence, the number of words in the Wikipedia article that we're processing, Q, K, and V will all be matrices of size L by D, where D is just some latent dimension that we've chosen. It's like a model hyperparameter. That means that multiplying Q by K transposed gives us a matrix of size L by L. And maybe you're kind of getting a sense of where this is going. We're talking about when L is really long. And as computer scientists like to think, what happens when our input grows? Well, the size of our matrix grows, which means we run out of memory and we spend a ton of time computing it. So computing scaled dot product attention, the time needed actually grows quadratically in the size of the sequence, can be actually worse. I think it actually may grow on the order of like L cubed, although I'm kind of blanking on what the actual runtime is. So that's pretty bad, right? We don't want the amount of computation we do to depend super heavily on how long the sequence is. It would be much more helpful if we can multiply K transpose times V first, right? That's an L by D times D by L, or sorry, that's a D by L times L by D matrix, which would give us a D by D matrix output instead of an L by L. So it's much smaller, much easier to compute. Overall, just much more computationally efficient. Does that make sense as to why that would help? Any questions? Essentially, we just want intermediate matrices that are smaller so that we don't have to do a ton of work to compute them and compute with them. So the idea here is performance through associativity. In the softmax equation above, or the attention equation above, if we like, in the ideal case, we would like to be able to multiply K transpose times V first and then by Q. Right, that's matrix associativity. If you've taken linear algebra, or maybe not, you know that matrix multiplication is associative, meaning you can multiply them pairwise in any order. So we can't really do that, and the only real reason why we can't is because there's this softmax sitting outside of it. If that wasn't there, we could totally do this, and there wouldn't really be a computation problem. So we really would like to find a mapping that approximates the softmax in the Q and the K. So we find a mapping such that the softmax becomes, or such that attention becomes this equation, Q prime, and then multiplied by, that is through associativity, K prime transpose V. And Q prime and K prime are this mapping, this kernel applied to the Q and the K matrices such that the softmax is kind of baked in. I'm treating this all at a really high level because, like, if you go read the paper, which I've linked, there's quite a bit of math, and once you read it, you'll understand why I didn't do it in this this slide. And now what we have is efficient matrix multiplication. We've gone from something here that was L by L times L by D, and we have to store this L by L matrix, to over here where we rearrange our computation. You can take R in this example to be approximately D, but essentially now we have essentially a D by D matrix and an L by D matrix. And then what we're left with is something that isn't massive in the size of the input. It only grows linearly in the size of the input as opposed to quadratically, which we had here. And so what we have is like a transformer that's much more efficient. And what we observe, and what this paper that is pretty recent observed, is that their performance scales linearly as expected. You can see the quadratic region of these transformers. The dotted lines are the regular transformers. The solid lines are the performer. The dotted lines start to diverge as the length of the sequence increases. And the authors of the paper were able to scale the performer up to longer sequences much faster and using a lot less memory. And they actually found in the second plot you see that they didn't suffer an accuracy hit, or at least not much. You'd have to read the paper to get a more detailed investigation of how accuracy changes, but it's pretty interesting that they're able to speed this up and still perform very, very well. Okay, so that's all I had about performers. I wanted to treat them at a really high level and kind of give you guys just an idea of something you can do and something you can read about and where the research is heading. So I think we've gone just about an hour, maybe like an hour and 5 minutes now. And that's all I really had for the presentation. So I'd like to ask if there are any final questions. And if not, I'll turn it over to Yi. He has a really cool notebook planned. So yeah, any questions? Okay, awesome. As always, oh, someone unmuted. No. As always, you're free to message me any questions that you have later. I know this topic is pretty heavy, but hopefully you learned a bit about how attention models are built and the benefits they bring, especially when addressing long-term dependencies. So with that, I'll turn it over to Yi to get you guys some practice about working with attention mechanisms.
All right, thanks, Joey. That was a really nice presentation. Let me share my screen then. All right, don't look at this. How do I move this? Okay. All right. So the thing that we're going to be working on today is, so if you open it up, don't look at this just